how we roll, man. Some rock, some win, some 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 win, man. Some rock, some win, some roll, man. Some rock, some win, some roll.
Hi, my name is Loris Crow, and we are executing a Showtime. Zig Showtime is the show where members of the Zig community come on stream to share coded ideas with the broader public. Every episode features two speakers who will present and take questions from you, the viewers. Zig Showtime is not just what you're seeing on the live stream, but also the discussions that you can have while watching. And that's why I encourage you to join one of the existing Zig communities that you can find by going to ziglang.org. Today's episode features two sessions that share a common theme, low-level programming. And when I say low, I mean it. Felix Queißner, also known as XQ on Discord and MasterQ32 on GitHub, will talk about his custom-made CPU and 80s-inspired home computer, while Noam Preil will present his compiler toolchain that can support and optimize custom architectures. As a small note before we begin, I wrote a blog post titled The Upcoming Future of Online Meetups, in which I rant about online meetups run on Zoom, and I also share a high-level analysis of Zig Showtime. So if you're interested, you can find my blog at christoph.it, and Nightbot has probably spammed the link already, and will also in the future. So now I think we can move directly into the first talk. So the first speaker is Felix Queißner. Felix lives in Germany, near Stuttgart, and he's a modern rebel. If you live near Stuttgart, you have to work for either a car company or one of the companies that work for car companies, like Bosch or Siemens. He's one of the few that works for neither, and when people asked him AMD or Intel, he chose an FPGA board instead. The talk is SPU Mark II, or How I Stopped Worrying and Coded My Own Toolchain. Felix, the stream is yours.
Yeah, hello. Loris introduced my stream title as well, so I can now continue to the next slide already. Who am I? Loris introduced myself a bit. So I'm a full-stack developer by day. I create desktop applications for our in-house use, like testing systems and so on. And I'm a crazy scientist by night, like introducing new programming languages, inventing stuff, building hardware, and building a computer. I love low-level programming systems. I love like old computers, retro computers. And my programming career started in game development, focusing on graphics. So one led to another, and now I'm a demo coder and doing low-level crazy stuff. I'm going to talk about my grand project, which is designing an own CPU architecture, as well as designing a whole computer around that. I started designing the SPU Mark II architecture in 2017, and as you can probably tell from the Mark II, it's my second version of the same architecture. And yeah, it's 2020 now, and it's time to build a computer around it, as the CPU architecture is ready to use. And thus, the Asher home computer was born. The Asher home computer is inspired by the late 80s home computers, like the Amiga 500, or probably the early as well, like the C64, so Commodore inspired. It uses the 16-bit CPU with a 24-bit memory bus, so it has an MMU. It has a VGA output for graphics, and it has serial port I/O. There are different features planned for the future, like having an SD card interface or a keyboard attached, so you can actually work on it like a really new computer. And yeah, that's a photo of the computer. I can zoom in a bit so you can see more. We have on the left a VGA screen displaying a wonderful screenshot of Commander Keen. And it's actually rendered by the FPGA board, which is the thing with the blue LED glowing. And we have a RAM connected to that, and we have a small like VGA graphics card dish thing, which is actually just a bunch of resistors doing analog digital conversion. So yeah, what are the bigger problems when you design your own computer? Well, first, CPU design is hard. You can see that like Intel is doing it for years and they still have bugs and complicated stuff in their CPUs. And the CPUs are humongous things of silicone, which do awesome computing stuff. And well, I started designing my CPU architecture in 2017, and now it's 2020. 3 years later, I'm actually ready to start building a computer around that. Why is that? Well, designing like a fantasy console is one thing, but having something that is working in hardware or even is remotely usable for long-term computation stuff is hard. And yeah, the other problem is having no toolchain means you have to use a hex editor and you have to use a lot of paper to actually assemble your code from a text representation into binary representation. And Zig helped me solving this problem by creating a whole toolchain for that. I have a debugging tool which is similar to GDB. It can halt the CPU, it can single step, I can peek and poke stuff into memory, I can enable or disable components of my computer at runtime. It's quite usable. I have an emulator which is crucial to implement your programs, because right now flashing my computer takes about 30 minutes per cycle, so iteration time is really slow if you want to test stuff on hardware, and testing stuff in an emulator helps a lot with increasing your productivity. Also, having an assembler is crucial to not doing a lot of paperwork. It helps me like assemble my code, and it helps me being productive as well. And this is what this talk is about, like how did I write my own assembler? I also have a disassembler which isn't really good, but it works enough to see if the assembler did its job. And now I can trust my assembler to just do what it's supposed to do. And there are also a couple of helper tools in my toolchain that convert like Intel hex files to binary files, that convert binary files then to VHDL files to be able to compile that for the FPGA and so on. And yeah. Now, to give you a small context about how my assembler language actually looks, it looks like this. We have comments, like in most assembly languages, introduced by a semicolon. We have directives to the assembler, which can relocate code, which can insert data, and we have instructions. And my instructions have a small thing called modifiers, which are these things in square brackets. I'm going to talk a bit later what those actually do, because it's really special to my CPU architecture. And yeah, I have like more directives, which is alignment, which inserting strings with zero termination, and so on. It's a full-featured assembler you can work with. And yeah, what does an assembler do? It takes this code and turns it into a binary, which looks like this. You can see that, well, this isn't really readable. We can see, hey, we have hello and we have world, which is the string from the previous slide here. And we can now look what the assembler did, like out of our push app message. This gets assembled into the push instruction, which is 0801, and followed by A1A80. The address of the hello world message here is 801A, which is, as the code is offsetted to 8000, is 18191A0D, is the carriage return here. And this corresponds to our app message label down below. So what feature requirements do I have for an assembler to be usable? Well, the first one is assemble code, and that's like the most basic feature you want to have, because without that, it's not an assembler. The second point is I wanted to have include files that allow me to share data or code snippets between different projects or programs. Like my BIOS is having a huge table of entry points into the BIOS and like magic constants. You can see them here. For example, app start is a constant that is referring to OX800, which is the entry point of programs in my computer. It should allow arithmetic expressions, like 1 plus 2 is an arithmetic expression, and it's not perfectly trivial to evaluate these, but it's also not hard. Then I need to embed binary data, which is like including an image, or in Zig, like add embed file. So I can include data pre-computed, like sign tables, images, also bigger text files, to just don't have them to code manually by, oh yeah, this byte and then this byte and then the next byte. Like, this is not convenient. And another quality of life feature is parser recovery or multiple error messages. Zig has this for, I think, a month now or 2 months, like where the parser doesn't error out on the first syntax error. And it's also a huge quality of life improvement to have several parser files, parser errors, instead of just erroring out on the first, then you recompile and you see, oh well, my next line has a syntax error as well. It's not convenient. And to talk a bit about assembling itself, what is assembling? It's turning text, which is the assembly language, into the binary, which is the machine language. I showed you before we have an assembler file and we have a machine language hex dump, and that's actually the job of an assembler. And it also is provides us with stuff like symbols, for example, with labels, instead of hard coding numbers in the code like I did before without my assembler. And that makes the code portable. That means it's not portable between platforms, but between memory locations. As soon as I insert an instruction into my code, every code after that is shifted in memory, which means, well, I have to recompute all addresses there, and an assembler is doing that for me. I'm also going to talk now a bit about instruction set architectures and how they differ. First, instructions are encoded in memory, like you need to tell the CPU what to do. And instructions have usually like at least 2 components, which are the instruction itself or the opcode. It's to tell the CPU, please add stuff, and the operands tell the CPU what to add. And some architectures, as far as I know, ARM and the Parallax Propeller architecture have conditional instructions, which means please execute this instruction only if a comparison was 0 or was overflowing or something. And somehow this data must be encoded in a binary to tell the CPU. And instruction architectures also differ in the encoding length of instructions. x86, for example, uses a variable length instruction set, which means instructions can range from 1 byte length to, I think the biggest is something about 60 bytes. You can have really huge instructions on x86, or you have fixed length instructions on ARM, which are 32-bit per instruction, and that's fixed for all instructions. All instructions are the same size. Fixed length instruction sets make decoding easy. Like, you want to get the next instruction, just add 4 to the instruction pointer and you're done. For variable length instructions, you have to actually decode the instructions to get the start of the next instruction. For an assembler, however, it's irrelevant if you use fixed length or variable length instructions, because the assembler emits them anyways, like from front to back. And my own CPU has a variable length instruction set, which is highly orthogonal. What does orthogonal mean in this case? Most instruction sets allow you to use some portions of register sets or addressing modes on some instructions, which means if you can do A with B, that doesn't mean you can do A with C, and that's making assembler coding a bit harder, because you have to think about if that instruction is actually allowed or not. And an orthogonal instruction set allows you to do everything with every instruction. And the SPU has one kind of instruction decoding, so every instruction is decoded and executed in the same way. And the decoding part is actually one of the things that makes the CPU special. And there is one field in the instruction set which is like the command field. You can see that below here, which actually defines what the CPU does to your data. And everything else in my instruction table here is like the executional conditional, the input 0, input 1, flag modification, output everything is the same for every instruction you can do. And only the command will differ for the CPU itself. So commands define what to do with the data you provide, which is like add or load data. Execution conditional means every instruction on the SPU is conditional. There isn't a conditional jump special instruction like on the Z80 or x86. Every instruction is conditional. You want a jump, you make that jump conditional. Instructions take 1, 0, 1, or 2 inputs, which you can configure with the input 0 and input 1 behavior. And that means you get your command down below gets 2 inputs, like arguments in Zig or other programming languages, and they return a value which is then modified by the CPU or processed by the CPU, it's defined how to process that return value by the output behavior. And here's another special thing. The output behavior has 2 major operations. One is push the data, which means you push the result of a computation to the stack, or you can jump to the result, which means the SPU doesn't actually have jump instructions. Every instruction is able to jump, and that's also unusual. And the last thing is the flag modification behavior, which means you have instructions like subtract, which can also modify the flags in terms of this, and you now can compare data with subtract. Yeah. So how does this look in Zig? Zig is quite helpful in doing low-level coding, because we can just take the table and put it into a Zig data type, which is here a packed struct. We have the condition, which is the execution behavior. We have input 1 and input 0. And we have the modify flags, which is a bool. We have the output, which is an enumeration. And we have the command, which is also an enumeration. Using a tagged enumeration here is useful because we can tag it with a U2 type. So the input behavior here is 2-bit, and the input behavior here is also 2-bit, which we can see those are 2-bit types. And yes, that's just like, it was hard in Z to make that portable and usable, and in Zig I just defined the struct and I was finished with all instruction decoding for the assembler or for the emulator and the whole tool chain. And it's really convenient. And now, how does an assembler work? Well, first, it's a tool that takes text and converts that to a stream of bytes. Every instruction read is appended to a stream of bytes, and it's outputted instantly. Which means I read an instruction, I translate the instruction, I emit the instruction, and I repeat that cycle until I'm at the end of the file. And that process is append only, so I cannot go back and insert data which moves all other data, because then I will mess up my internal instructions and offsets. And we have one problem with that, which is forward references, which means what is happening when I'm doing a jump forward in code, like jumping from the main function into a sub function, and the sub function is in memory behind the main function. When I'm assembling, I keep references like symbols to stuff, and if I encounter such a symbol when assembling and I don't know it, I have no idea how to resolve this at a moment. So the solution to that is you have either a two-pass assembler, which is pretty much we read the whole file and we decode it and we store all symbols. Then we go back to the beginning of the file and we start encoding the whole stuff again, and now we know all positions of the symbols. Or we're going to use a patch list, which is, I have found a symbol and I'm now going to insert that into the patch list, and I will resolve that later when I know the symbol itself. And what problems did I have with the assembler? I have code with holes, which means I'm having code starting at 0 address, and I have code starting at 0x8000, which means like the half of the memory, and there's 32K of memory in between. And yeah, how do you solve this? The other problem I had was how to solve arithmetic expressions. I talked a bit earlier about it, that it's not that easy, but it's also not that hard, and I'm going to tell you how to solve this. The other problem every assembler has is the forward references, which I explained already a bit. And a problem with my CPU architecture is the too many instructions problem. And I'm going to tell you about that also. So, how to solve the empty space or the holes in the data stream. And that is done by sections. It's not like the sections you know from ELF files, which is like .data or .text, but sections are substreams of data in the assembler itself. And a section has an offset in memory and then just a bunch of bytes behind that offset storing the data that was assembled. .org is a directive to the assembler that creates a new section, and every time you write a .org, I'm creating a new section, appending that to a linked list of sections, and start assembling into the new section I created. Which means, in the end, I have a lot of sections. Some of them are empty, and all empty sections can be dropped. And I have like a sparse memory map of the stuff I wanted to assemble. Arithmetic can be solved by the shunting yard algorithm, which is, as far as I know, invented by Dijkstra. He's also the guy who made like this famous pathfinding algorithm. And shunting yard algorithm is really easy to implement. You just need a stack of values and you have an output stream, and the algorithm itself is explained on Wikipedia pretty good. So just look it up. It's a nice thing to know and to implement in your own project. It's a good exercise. One problem with shunting yard, though, is that it doesn't really do syntax checking. So you can just write pretty much any sequence of symbols, and it will just take it and transform it into something that is roughly right or not, if it's not syntactically correct. But for me, that was okay. It's an assembler mainly for myself, so I can live with that. My solution to forward references is the patching, and I explained earlier how that works. We had 2-pass assemblers in the past a lot, and 2-pass assemblers were used because we couldn't have the whole program in memory while assembling the whole program. Which means if we have a machine with 64K RAM, we cannot assemble a program which is 64K byte large. But on a modern machine, like anything built after, I think, 1995 or something, we can just ignore that problem and store the whole memory in RAM. So patching is way easier to implement, and it's also faster in execution. And how to implement it is you have your section list, and you have a list of patches per section. And the patch is storing the offset where to patch your binary later, and the expression that needs to be patched. So when you encounter an expression while assembling, and you cannot resolve a symbol in that expression, you just put that expression and the offset where it should be put into a patch list, and you write bogus data, like I think I'm using AAAA in hex to just note that there is something wrong. And at the end of the assembling process, you just resolve that list, meaning you go to the list, you resolve every expression again that wasn't resolved before, and you write the data into at the position which you stored, or you do an error if it's not resolvable in the end. And on a problem on my CPU, it appeared to me that having an assembler is easy, but then I noticed that I have 32K possible instructions on my CPU, and you cannot remember that much instructions in any way. And my thought initially was to make instructions with the same prefix, which means for every command I have, which would divide the set by 32. And well, it still yielded 1K instructions per command, and that's just too much. And my solution to that is those particles, which are the modifiers, I call them, this. And it allows you to change bit fields. So we have this structure, and each modifier is able to change one of these fields in the assembler. So we have an instruction add, and we want to override the input 1 field, and we just use the square brackets. We use I1 to mark the input 1 modifier, and we use peak to set that field to peak. And now we get an instruction which does input 0 is pop 1, input 1 is peak 1, then this instruction adds them and pushes the result. And it's really unusual to work with this, and assembler coders are, I think, a bit disoriented at first when they see this, because it's really uncommon to have this, but I don't see a better solution to this problem. And it reduces the whole problem space to 54 modifiers and a handful of predefined mnemonics like the add, which usually pops 2 values, adds them, and pushes the result. And now I'm going to show you how the usual workflow with the assembler itself works. And this is a small program which Loris inspired me to create. We have the org, we have some setup here, and we have an implementation of a C function down below. And this is how the assembler looks. And we can now use the Zig build toolchain to assemble the file. We can now look into our result, which is the Intel hex file. This is the output of the assembler. And we can put that into the emulator and run that, and it creates a beautiful maze. Yeah. How the code in the assembler itself looks, I want to show you some highlights. The code itself is like 2,000 lines of code, and I don't want to walk you through all of that, but the basic process. We create.
Felix, if you can see if you can increase the font size a little bit.
Oh, yeah, I'm going to try that. Okay. So we have the assembler object itself, which is a Zig struct, which keeps track of all assembling stuff and does some bookkeeping. I'm going through all files passed on the command line and pass those files to the assembler using an instream, which allows us to call this function recursively to allow the include files. And after processing all files, I'm going to use the finalize function, which applies the patch list we built. Then, if we had any errors, we are going to return these. And otherwise, we're going to write a Intel hex file to the output, and we're happy. And two things I want to show. One for understanding the assembler is the finalize function, which goes through the, I think it's a hash map. No, it's a linked list here. And it goes through the linked list of sections, goes through the patches per section we have, and it will now evaluate expressions. Either it will create a missing identifier, that means we cannot resolve that patch list, or we're going to have a value here, and we're going to patch the value just right into the memory, which is done with that. And another thing is an elegant solution made possible with Zig. We can use structs and comp time to iterate over struct fields, and I used that to create my directive parsing. So the parser of the assembler, as soon as it finds something that starts with dot, it searches in the directive struct for a function called dot symbol, and it calls that function to parse that special directive. In this case, I'm having the function that parses the org, which creates a new section. I have a function that parses the .ASCII, which creates a string and emits that in memory, and so on. And using that is pretty easy in Zig. We have we encountered a directive, and now I'm going to iterate over all my function declarations in directives and call that function here. And I think that's pretty neat and a nice solution possible in Zig, because the comp time reflection makes it a lot more easy than before in the C++ assembler I built, which was horrible. And this assembler is actually quite clean and expandable. And yeah, a short summary of the talk is building a computer is hard. Really, you have to think about a lot of stuff. You have to know a lot. And I learned really much starting to build the Ashet. What I also learned is building a toolchain with Zig is not hard. The emulator is, I think, 300 lines of code, and I wrote it in about an hour. And I really think I wasted hours in writing the assembler in the emulator in C, because it is hard to handle overflows correctly. It is hard to handle everything in C is more complex than using it in Zig. And what I also learned is like write expressive code and write code that is simple. And you've seen that we have a function called .org, and we can just call it to parse the .org directive, and it's clear what this function is supposed to do. And also build the tools we need. Zig allows us to build a lot of tools. It allows us to build fast tools, and I'm really happy with that. Yeah. If you want to know more about my project, visit ashet.computer for more information. There's also an online emulator you can use, and you can get the whole toolchain and source code for the project there. Yeah, thanks for listening.
Thank you very much, Felix. That was an awesome presentation. So let's move to the Q&A now. Just a reminder, to ask a question to Felix, remember to tag me in the chat message. And don't forget that I'm looking not only at Twitch chat, but also at Discord and the Zig RC channel on Freenode. So each of those places is fine. So let's now move to the Q&A view. Okay, so Felix, while people think what they want to ask, let's start with the most basic question. How did you discover Zig?
I think I was ranting about C++ with a friend of mine, and he was like, hey, by the way, I've discovered this new language. It's called Zig, and look it up. It may be something for you. And he was right. And I started reading the spec, and I immediately fell in love with the language.
Okay. Wow. So a friend recommendation and you took a chance.
Yeah.
I see.
Exactly.
I see. How long ago was this?
I think it was last spring. So 1 year ago, roughly.
Okay. Okay, cool. So, by the way, another question that I had in my mind, the maze was really nice.
Thanks.
Yeah. So I saw that the C function that you pointed out that you had translated, the source shift, that's basically your
that's
pseudo
the
random.
generator.
Yeah. Maybe let me take a look at it a little bit again. I'm going back to the first view so that you can share your screen. Okay, so it's very simple. It's just shifting.
It's
around.
shifting and doing XOR, which is like the name of the function.
Okay. And you're just seeding it at 1.
Yeah.
Okay, that's cool.
It's actually taken straight from Wikipedia, and I translated it to my own assembler language, and yeah.
So there is one question on Twitch from Rust Compiler. So the Rust Compiler is asking, why should someone switch or write a new project in Zig? Well, what are the main benefits over C++ and Rust?
For me, it's simplicity, and that is like shown in all the code. And you just go and you write your stuff, and it usually works pretty fast. And I used to write programs in Rust or C++ too, but I spent way too much time thinking about how to implement something instead of just doing it. And in Zig, the path is clearer because there's no like super high-level abstractions, and you can just go the direct way instead of thinking which abstraction do I choose, how do I structure my classes, and you just go for the code, and it works usually, and it works pretty stable. And yeah, that's the point for me why I switched to Zig. It allows me to work roughly 3 to 5 times the speed like in C++.
When are you going to introduce Zig to your company?
Pretty much at 1.0. I've talked about Zig with colleagues already, and I said, yeah, I'm really going to push that when 1.0 is out, because every one of you will love this. They're all C programmers, not like C++ programmers, and they're all like, oh man, this undefined behavior stuff is hard and we know so less about it. And yeah. And I think Zig will help there as well.
Okay. Let's see. We have another question. What does it mean to assemble hardware and toolchain for it? Is it on the same level of what Intel or AMD does?
Well, basically, I'm using the same processes as them, but at much lower level, because my CPU architecture is simple. It has less bits. It has no pipeline. It has no caches. It doesn't have the complex stuff. But as far as I know, the processes I'm using, like using FPGA to simulate and using self-written tools, is the same as they do, just on a not that complex level.
Okay, a bit of a joke question. What's the status with Spectre and other vulnerabilities with your CPU?
Yeah, I don't have them. My CPU doesn't have like those weird vulnerabilities because I don't have the features that enable them. So go with the SPU Mark II. It doesn't have Spectre. It doesn't have Meltdown. It doesn't have cache misses because there's no cache.
Nice. If there's any cloud provider that's listening to this talk, I'm sure they will make sure to contact you, and you'll probably get a multi-billion-dollar contract with them for sure. Another question, this one from chat. What would you like to see implemented or added to Zig before it hits 1.0?
Well, for me, it's probably both issue 1717, the function syntax unification, as well as the packed struct fixes, which I hope will come with stage 2 soonish.
Mm-hmm. Okay.
And yeah, otherwise I'm really happy with the language in status quo.
Okay. Cool. I think we got all the questions. That was pretty cool. Can you show one last time the maze?
Yeah, sure.
Let me transition first.
Oh yeah. One problem with my emulator, I cannot stop it when it runs and it doesn't do keyboard input. Yeah, it's using raw keyboard input instead of cooked keyboard input, and that means Control-C isn't going to break the process, but it's just inputting the ASCII character 3.
Mm-hmm.
And that means I have to kill the process from outside. But yeah, here comes the maze.
Nice. And is the printing speed, like, are you sleeping, or is that the emulation speed?
There's actually a pretty heavy idle loop in here, which waits 16,000 cycles.
Okay.
So if I remove that, we can just reassemble the code.
Can you also seed it to another
and
seed?
Run it, which is done.
Can you also seed it to something else, like 42?
Yeah, sure. We can like seed. I'm preheating, so we can preheat it to 42. And assemble, run, and we have another maze.
Nice. Okay, thank you. That was awesome. So let's... Yeah?
You're welcome.
Okay, thank you very much. We can now move to the break. As usual, we have a 10-minute break. I hope to see you at the end of it, and we are going to have another talk by Noam Preil now. So, see you soon. Okay, the second speaker is Noam Preil, also known as Pixel Hero Dev. Noam is from the US and he studied electrical engineering. His talk is about a compiler toolchain he's working on, and if you're on Discord the last couple of days, you probably already know a lot about it. The talk is Project Tricarbon. Noam, the stream is yours.
Right, so before I can get into the actual project, I wanted to explain the motivation behind it, and to do that, I need to explain why I had problems with all the existing toolchains. A key goal I had was that it should be usable for both compilation and emulation, not just one, not just the other. GCC, for instance, and LLVM, they have a JIT toolchain. You can use them for emulation, but they're not very good for it. So there's a lot of shared code between the two. It shouldn't be wasting any efforts. Every feature needs to have a justification. I don't want any extra features, nothing that isn't 100% needed for what it's doing. So no two features should cover the same scope. Nothing should be necessary. Every single line of code should be there for a reason. Generated code has to be fast, but so does generating it. So if you generate the most efficient code ever, twice as fast as GCC, but it takes you 2 years to do it, it's not worth it. Clients should have full control over every single step of the process. So if I'm writing a JIT and I want to tweak some random internal, I should have the ability to do that. I shouldn't need to worry about it not being marked public. Completely arbitrary backends should be usable, whether that means something like a Harvard architecture with separated RAM, ROM, a system with no registers, a system with only registers and no memory, whatever it is, it should be supported. And it should be completely modular. Every piece should be able to work on its own. They should augment each other instead of depending on each other. LLVM is not particularly great for these purposes because while the IR is actually really good, the library is less so. It's just a whole bundle of C++, which might not be a problem for some people, but when you're trying to work at a different level, for instance, in Zig or in C, it's very annoying. They have bindings, but it's very clear that non-C stuff is not that non-C++ projects are treated as second class. And while the produced code is pretty good, the compile time performance is not. Weird backends are very annoying to add, and of course, it's not written in Zig. There's definitely a problem with it, definitely part of the motivation. It is usable for emulators, but only technically, and as everyone knows, any sentence that begins with technically can just be ignored. It is nowhere near simple enough for my purposes, and while it vastly exceeds the runtime performance goals, that's just one factor. Compile time is awful, and the performance at runtime is not everything. The same way I like to say that safety is not the most safety might be a very important goal, but if you have the most safe project, but it's not able to run at more than one instruction per second because it's constantly checking unnecessary safety features, and it doesn't matter. It needs to also be able to function properly. Similarly, here, compile time performance is also very important, and meeting one of the factors is not nearly enough. While the libraries work at the C++ level and there are C bindings, it is unnecessarily difficult to integrate with other projects. QBE is better, but it's not quite there. It's also less well known, so I'm just going to give a quick rundown. The goal of QBE is to have 70% of the performance of LLVM or GCC in a tenth of the code. It's able to compile in half a second even on older hardware. Currently, it only supports AMD64, nothing else. It's written in C99, but the actual C library isn't there yet. It's hackable, which is good, and it's much easier to work with. And honestly, I probably would have just worked on QBE directly instead of doing my own, but that would probably have been less fun. And I had some differing design decisions also. It meets the goals of performance and simplicity for both compile time performance and runtime performance. I do not believe it is usable for emulators out of the box, though that could probably be fixed. Platform support is, of course, poor, and just like LVM, it's not written in Zig. No breaker there. So my solution is I'm going to make my own toolchain from scratch. This will end perfectly. Sorry, this is definitely not going to exacerbate the issue in any way. I don't see why anyone would think that. Some of the key ideas behind the Project Tricarbon stuff is that emulation is a first-class use case. It's not just a side point. It's not just you can use the same stuff. It's there. It's a key goal. It should be just as nice to work with for emulation as for compilation. There should not be any duplication anywhere. The components used for compilation and emulation should be the same. Backends should not have duplicated code, but should share common components. And it should be, at least to some extent, provably correct at compile time. It should be able to prove that the final binary matches the source code. This is arguably a trusting trust variation because in order to be able to prove that, you have to prove that the compiler which is used to produce Tricarbon is itself correct. I'm ignoring that because that's not relevant. It should not do any work it does not have to. So if there's an optimization that buys like 0.01% performance, there's no point in doing it. Don't even bother. If there's some step in the process that can be eliminated and replaced with something simpler, don't do anything that's not completely necessary. Quality of the code matters, not the language it's written in. I'd rather have high-quality C code than low-quality C++ and vice versa. I don't care what the language is, it just does not matter. One rule is that all of them have to share the same ABI, and because this is the current C component from the last decades, it has to be the C ABI. Whether that's the System V1 on POSIX or the MS Build one on Windows, they have to speak the same ABI. This means that if you're writing in Zig, everything has to be exported. You have to have the exported API as the priority. And for C++, everything needs to be marked extra in C, and so on. It also should be able to handle completely arbitrary IR formats, ZIR, QBE, LVM, and so on. All of them should go through the same pipeline without any changes, which should be able to convert them into one common format using a generalizer. Some of the inspiration was Lefticus's 86 to 6502 transpiler. I stumbled upon this at one point a year or two ago, I think, when I was working on a Z80-based emulation system. And I made the mistake of trying to port it to Z80 instead of doing one from scratch. That was a mistake. But it stuck around in my memory for a while. It's an interesting project, able to compile C++ as the 6502 using GCC or Clang, and just translating the assembly itself. Another project that I drew a lot of inspiration from was MIR, or the middling IR. It's basically the same thing I'm doing, or QBE is doing. It's an alternate toolchain from scratch, except MIR is a lot closer to what I'm doing. They are planning on, for instance, parsing LVM and using that directly, and so on. One of the things I learned from that is that disabling optimizations in GCC or LVM for JITs just does not help, because the time for it to assemble an empty file is simply too long. Oh, there we go. On an Intel something or other, i7-9700 or something like that, an empty file takes nearly 8 milliseconds to compile with optimizations disabled. Turning them on doesn't really change that. Level is not enough. The initialization time is the problem. It does not matter how quickly you can run after the initialization if translating a block takes this long. It's just intolerably slow. A quick overview. Cross-compilation is a first-class use case, which you might recognize from the Zen of Zig, or maybe it was the Ziglang website. Either way, all compilation is treated as cross-compilation. To achieve that, I'm using RISC-V as the IR. Not directly, or not at the first step. It takes in, like I said, LVM or QBE, generalizes that, and then does some basic work on that and produces the RISC-V IR. Then this is used for the rest of optimizations, translations, and so on. A custom RISC-V quote-unquote extension is used to provide fused operations, but I put extension in quotes there because it's not really technically a RISC-V extension. It's more like it's treating multiple instructions as a single one in memory. If it actually writes it out as RISC-V, it still produces completely canonical RISC-V machine code. There is an actual custom extension used for instance, register sizing. So RISC-V, I'm using a 32-bit RISC-V base, which means that all instructions operate on 32-bit registers. There are only 32-bit registers. It's not like 86 where you can access them as 8 or 16-bit components. They're always 32-bit. To make CodeGen more efficient, what it does is it allows for certain instructions to basically say, from now on, treat this one as if it's smaller, which means always assume the top bits are zeroed because we're never going to let them be set. This can be used to optimize in various different ways, but it's also just it's more efficient. No, like I said, don't waste any work. So yeah, front ends only have to target a single backend. So if you're writing, for instance, a Zig front end or a ZIR front end, it only has to target RISC-V. You don't have to target AMD 64, ARM, MIPS, and so on. You only have to target a single one, which means writing that front end is easier. And one analogy I like to use here is consoles versus PCs. Consoles aren't better than PCs because they have better hardware, though they often do. They're better because they're 100% consistent. Every single one has the exact same hardware, which means that if you're writing a game for it, you can optimize specifically for that hardware, and it does not have to work on anything else. It's the same thing here. The front ends do not have to worry about anything other than the RISC-V. That is it, which means that they can do more efficient output there. And then the RISC-V can be proved to be correct. Basically, if you can prove that the RISC-V matches the input IR, then you can prove that the output, the final machine code, for instance, this 64-bit AMD 64 machine code, is exactly the same. The IR can also be manipulated using common tools because RISC-V, there are just RISC-V tools out there. You don't need to make new ones. And register allocation when writing an emulator is effectively a knob. It is cheap, it is easy, it is simple. You don't even have to worry about it. And translation's pretty simple too, especially for RISC like ISAs, but even for other ones. So yeah, it's also easier to interpret the RISC-V than to try to interpret LLVM-IR, for instance, because it's an actual ISA and it is completely interpretable, whereas this is not. So this allows to prove that the machine code that is correct. The IR can be interpreted while running the final machine code step by step, the same way GDB would, and you can prove that the high-level variables are the same. It's not about checking the registers or anything like that. It can say, okay, we can map a variable in the source code to this register in RISC-V and to this spot in memory on the AMD 64 code. So let's just test the values after every instruction that modifies them, make sure everything is exactly the same. And that's where Thor comes in. Thor is one of the Tricarbon components. It translates RISC-V to arbitrary backends, currently AMD 64 only. And yes, I know I complained that QBE only supports AMD 64, but the issue there isn't what it supports now, it's what it can support in the future. QBE is explicitly designed for AMD 64. There's ARM support is planned, but that's it according to the website, and that's just not enough for me. So Thor is also designed to support, for instance, the Z80, which is an 8-bit ISA without any issues, without needing to change anything that's done. This is one instance where register sizing comes in. If you can say all these registers are 8-bit, you don't have to worry about the upper bits. You can treat the data as the correct size. To allocate the RISC-V registers to host ones, it uses a linear scan register allocator, which basically means it goes over the code from the RISC-V from start to finish, and it makes a list of which registers are used when. So what it does then is it says, okay, this register is needed from point A to point B, this other one's needed from C to D, and then it just allocates a register to each. If whenever that interval, that Hive range is over, it frees up the host register so some other value can use it. And since currently the target is AMD 64, which has about 14 usable 64-bit registers, unless you're using 14 values simultaneously, you're not going to run out. For other systems, it'll have to do, for instance, register spilling, moving them into the stack before you use them again, but that's not the concern for just yet. The reason I went with linear scan allocation is that it is vastly simpler than the graph coloring method that is used by GCC and LLVM. Which means that the performance when running the allocation is much faster, significantly higher, which means improved JIT time, and for most compiled code, it's going to be just as fast too. Another component is what I'm calling now the unnamed backend project, because I originally named it Lightsing as a pun on the new Lightning project, before realizing that was a terrible idea, and using a joke name was not a good long-term option. So yeah, it's temporarily nicknamed Lightsing because I'm a horrible person, but Lighting did a better job with the pun because or Lightning, was there an EN in there? Either way. So eventually, it was originally part of the same project as Thor, but I eventually split them apart because each one has a narrower scope now and they're more modular. If I want to write just a raw 64-bit assembler, I can just do that without needing to worry about the other components. backend works is it has an instruction builder that creates a list in memory of what instructions are there, and it determines the sizing while building them. So it basically decides which variant of an instruction to use ahead of time. It also processes labels correctly, so you can give it labeled code and it will work. Unlike Felix's two-pass assembler, the way this one works is just single pass. When it creates a second list of labels and a third list of references. So the assembler basically creates an in-memory object file, an object file-esque structure, which has the references, the labels, and the actual instructions. There are no optimizations performed by this whatsoever. Those are done at a higher level. Those are out of scope. It should be as simple as possible. If I want an assembler, I don't need it optimizing. I'll do that myself, or I don't want to do it at all. There is no real linker, and that's a design decision. Like I said, it's out of scope. Don't add any unneeded features. So when compiling a proper if you're compiling a multi-file source input, like a 10C file project, you're going to need an external linker. You can, however, if you have like a single file the way Zig does, you're not going to need one anyway because everything's internal. There is a mini linker which can resolve internal references because it has the list of labels and references, so it's able to match them up and just trivially replace them. This is useful for JITs and for single file compilations, and it's much simpler to implement. I think it's literally like 15 lines of code at most, which is nowhere near the complexity of a proper linker, which means that it can have most of the effects needed without the costs. Some potential ideas for the future were hot swappable register allocators, similar to the way that Zig is planning an optimized for built-in. So you can say, I want this to be fast, I want this to be safe, I want this to be whatever, I want this to be small. You should be able to say, well, I want this specific bit of code. It's going to be a very tight loop. I need it to be the generated code as optimized as possible. The compile time here isn't as relevant because it's going to run a billion times and only be compiled once. Or you could say, this bit of code is literally only running once. So, you know what? I don't even need a register allocator here. I'm going to use adaptive optimization. Instead of, for a JIT specifically, instead of actually translating to the native architecture, it can, in theory, interpret the RISC-V directly, producing the correct results. This is, I believe, something that Hotspot JVM does and other projects. It means that you only use the JIT where you have to. Another idea I had was for a Linux package manager, which uses the RISC-V IR as the binary form, already optimized. Everything statically linked, tracking dependencies, fully relinking whenever a library is upgraded, which removes the single biggest problem that people have with static libraries, if I remember correctly. And since the RISC-V that shipped is already optimized, the only optimizations that you need to perform when it's installed are the native ones. Basically, you can replace some code with whatever's fastest on the current hardware. You can say, I have AVX 256, let's do some vectorization, and so on. The idea would be to have the performance of a source-based distribution like Gentoo in a binary-based operating system. That's a long time away, though, and for now, continuing from Felix's talk, I have created a SPU Mark II just-in-time compiler. It found various bugs in Thor, literally dozens, I believe, along with the backend. Now, there's now 16-bit instruction support, and the register sizing is sort of, kind of, but not really implemented. So it's just sort of making it up in the backend instead. And it already has the automated test suite. Similar to the one I mentioned about interpreting the RISC-V, this does basically the same thing for the SPU2. It's sort of a proof of concept to make sure the idea works. It runs the interpreter. I ported the interpreter, largely based on Felix's. I needed this for the test suite, so I just made a new one. One key difference from his is that there's a shared bus with the JIT. Instead of duplicating the code, all of the ROM loading, the logic to write and to read is basically shared between the two. Serial output and input, tracking memory, it's all one thing. It's specialized at comp time. So yeah, that allows deduplicating a lot of the code. And the one key feature about the JIT is it uses fast memory. All virtual memory is mapped into the host at a static offset, which means if something is in memory on the SPU as address 10, It's on the host architecture as address 0 by 10,000 hex plus 10, or 65,546. The reason I chose that offset and not 0, which I was originally going to do, is that I'm running a hardened kernel, which means that I am not able to map in memory by default at any address lower than 65,536. If I try, the operating system says you're not allowed to do that. This is for security reasons. If there's a bug in the kernel and it tries jumping to null, and I've mapped in malicious code there, it means that I now have kernel mode access, which is not something you want. I can actually override that and let myself put it at a lower address, but this is not a good idea for anything meant for other people to use. And it means I'd have to go to root every time I want to run this, which not a good idea, or every time I boot the system to run it. And yeah, that's basically all of the slides I prepared, because for now I'm just going to focus on the actual code and how things work. One quick example is the test suite. The way this works, it's running the interpreter and the JIT side by side, and this is emulating the first test that I have, 1.hex, running one instruction at a time, going over and over and over, and then just verifying if registers, verifying memory, and so on. That's the maze test that he was running. In order to avoid it being a mess, it's actually muting the interpreter first, so only the JIT is showing any output there. But yeah, it's the first file basically just wrong one. The first file prints out hello world and then does a busy loop printing out 1,000 exclamation points. This one can run at about 5 seconds currently. Oh, is that the interpreter? That's the interpreter. Why is that the interpreter? Because it's configured wrong, probably. Doesn't matter. So yeah, what this is doing is it's running this it's running it twice at the same time. One instruction after another, after another, after another. The way the test works is it maps in the sets up the JIT bus, it sets up the interpreter bus, sets up the actual CPUs, and then what it does forever until it reaches the target specified in the test definition, or it hits a specified limit saying you're not allowed to run that many blocks. It should be done by now. It will keep running both. It runs the recompiler, runs the interpreter, verifies that the registers match, verifies that the bus state is the same, which this measures, for instance, serial output. Meaning it checks that the same value is printed by both. For instructions that modify memory, it also checks it checks a couple instructions near the stack pointer to see that it gave the correct results. So yeah, it's able to check for any mistakes in the RAM, in the registers. It's able to just prove that the JIT has the exact same effects as the interpreter, not just internally, but on external state too. Easy to define. It's just give it a file, give it how many instructions to run at a time, where to end, and it'll just keep going. For the test, it actually mutes the exclamation points because there's no reason to spew out 2,000 of those. So it just counts how many it did, keeps going up and up and up, and eventually the test finishes, test passes, goes to the next one, on and on and on. It gets to the maze, which doesn't actually succeed right now, but that's not the point. There is timing. With the interpreter, one key idea here is to check how fast it's actually going. Because if it can't at least outmatch the interpreter by a very large margin, then there's no real point. The generated code has to be at least somewhat efficient. Currently, the generated code is actually pretty bad it's not optimized at all. So with the interpreter in the fast mode, it's able to do that first test in 4.6 seconds. With the recompiler, which takes a bit longer to build because of course it does. I'll just come back to that. So the way that the interpreter works is basically the same as the way that Felix's works. It goes over the instructions one at a time, reads values in from the bus, writes them out. And one actually one notable Zig feature that he touched on that I actually took a step further. I have the CPU instruction structure defined. I literally just have it copied from his project. Condition, input, and so on as packed structure. Now, what his interpreter does, if I remember correctly at least, is to read an instruction, it fetches it from here. It reads it as a 16-bit value, and then it bitcasts it. I took that a step further. The read function I have is generic on the type. You give it the type to read. I didn't even plan it out this way. It was originally just so you could read between 16-bit or 8-bit. You give it the type to read and the address, and it will automatically read it as the correct type. Not worth a bitcast in it per se, but for the JIT at least, it literally just interprets the memory directly. It creates a pointer to it and just reads it. And that was a really neat feature. It's able to just give it the type and it works. You don't have to worry about the cast. It'll handle it correctly internally. Here we go. Now that this is actually built, the interpreter took 4.6 seconds. The JIT took 1.8, and this is still very inefficient code. It should be significantly faster, but it's currently not generating the smartest code by any measure. So yeah, the way that the interpreter works is straightforward. You check whether to execute based on the conditions. If you execute, you read in the inputs, and you generate the outputs, and it's just straightforward. The way that the recompiler works is slightly less so. First off, the biggest feature is the register allocator. Biggest not in terms of size, though that's probably true too. It's actually, it's a lot smaller now. Cleaned it up yesterday. What it does is it maps in registers or virtual memory to a RISC-V register, which is why it uses a U5 as the type, basically. There are 32 RISC-V registers, so it just uses U5 to mention to keep track of which one. It keeps track at all times of all 32 RISC-V registers, whether they're mapped to anything and whether they've been modified. Register, it goes over all of them, finds one that's not modified, and marks it as a temporary, and just gives it back. Otherwise, there's an error because there's not enough, but I don't think that's actually happened at any point. When you're done with the register, you give it up. It can store it implicitly. Getting a register is just straightforward. Go over the mapping, find one that's mapped to a virtual register, find the right ID. Getting do the same thing. It tries to get it. If it can't, it tries allocating a new one, marking it as the register. And if you told it to load in the value, I care what's in there, then it actually loads it in from the JIT's IP thing. It loads it in from the actual position counter in the JIT or whatever other variable register you're using. There's also a store used function which goes over all of them and just stores them one after another, and so on. These will be important shortly, but not just yet. To actually translate code is pretty straightforward. The instruction pointer of the SPU Mark II CPU is statically allocated to the RISC-V X1 register, which means that it doesn't even need to be loaded in. It's just always there, which is pretty much just a micro optimization because it's used in literally every block. There's no reason to ever bother allocating it. For instruction count you give it, you tell it how many instructions you want it to translate. It will do that however many you told it. You can also tell it to just keep going until you're done, until you hit a branch, by giving it null. So it reads in the instruction the same way the interpreter does. If it's in debug mode, it dumps out some useful information, what instruction it's translating, what the inputs are, and so on. And then we get to some of the more fun parts. Instead of being able to say, do I execute, the way the interpreter does, the way the interpreter works is it checks is the condition true? If so, I want to execute. The way the recompiler works is kind of the opposite. Since it's generating code, it can't just check, is that condition true now? It has to check, is it true when this generated code runs? So it loads in the flag register to check, it loads that in through the register allocator. It sets aside a temporary, and when it's done with it, releases it. And then it basically generates some simple instructions. It generates an AND, which means that the temporary register now contains the first bit, what's the 0 bit of the flag register, and then it does a conditional branch. If that's 0, if it's false, then it jumps ahead by 2 plus the use count. The use count is however many instructions will be produced by a store use call, which means that this effectively jumps over from the start of the next instruction here, the load register. It jumps 1, store used, and 2. It jumps over this. One of the neat way this works is you give it an offset. The target is currently used as an offset from the current position in terms of the RISC-V instructions. So internally, this gets translated, this branch. The way this works is it creates a new label, generates the branch in the builder, and then adds that label in because it needs the label because it needs to know the current position that tracks where it started. And this basically tells it, okay, so when you get to that label, when you are generating this in the actual assembler, this is the target in terms of RISC-V instructions that you're going to want to go to. Then the Thor translator actually produces that correct value. I'll do that later. So yeah, and then, so what this basically says is, if that condition is true, jump over this bit here. What this bit says is, if the condition is false, we want to load the new address, the new position into the register, and then we want to store them all and jump to the exit. We're done. So basically what happens is, if execute is false, it exits the translated code entirely. Otherwise, it continues on, and that's true for all the other conditions too. It's the same thing, but with different values. Then for the actual instruction, if you're executing it, what it does is the 0 register, if the input is 0, it's just mapped to the RISC-V 0 register, which literally always returns 0 on read and can't be written to. For immediates, it allocates the register, loads in the value. For the other options are peek or pop, which means you're getting a stack value. So it loads in the stack pointer, offsets it to the physical address with that 10,000 offset I mentioned. And then it does a load 16, which means that it takes that address and loads 16 bits from it into that register. If it's a pop, it then also modifies the stack pointer and continues accordingly, and marks it modified so the later store use cleans it up. It does the same thing for the second input to the instruction, and then for the output, it does the same work that the interpreter does, but it generates it instead. So for instance, if we're assign extending a value, which means that if the this is for the lower bit, right? Yeah. If the 8th bit is set, then it's negative. Otherwise, it's positive. It extends it the same way. All these instructions do the exact same thing. They modify register allocations, get all the work done, and then same thing as the interpreter. Based on the output, either we ignore it, we push it to the stack, or we jump over it. And that's basically it. The flags are modified, but everything is exactly the same. When we're done with the full translation, oh wait, that's actually done. The G is gone. If we haven't jumped anywhere, then we load the current position into the position counter, and then we store all the registers. This stores the PC, stack pointer, flags, and so on, updating them in the host effectively. Then it tells Thor, do all the heavy lifting now, which is sort of where the name came from, but not really. So Thor does all of the translation. It takes RISC-V, allocates it to the 64-bit registers, translates the machine code, assembles it, and does the mini linking. That one's not working, but I don't need it because I have this. That goes through here. And it basically just tells the assembler, go through the list of internal references and resolve them. That's not needed. That's not needed. It goes over the internal references and finds in the list of labels and inserts the addresses correctly, offset, and that's it. Then once all of that's done, once it's translated, what it does is it gives the result back to the host. It finds the physical address of the generated function and gives it back to the host. So, which then has a cache for it. So it basically says, if we already have it cached, let's just run it. Otherwise, translate, run it, add to cache. And that's basically it. That's all there is to it. The actual, as Felix mentioned, writing an interpreter for this was straightforward. At most took an hour. It's really simple. The actual JIT was very similar. The only part that needed to be redone was the translator. The rest of it I was able to literally just copy from a different project I had. This whole thing's 600 lines, and it's very, very similar to the interpreter. The logic is all the same. This requires a slightly different method of thinking. One last neat feature to show off before I'm done is this. In order to load in a value, the way the interpreter does it, is it just directly calls the read function. But this can't do that because we need to read it in the generated code. What this function does is it generates a call to a function in the actual host code, not a generated call. You give it the list of inputs and outputs, and it literally generates a call to these functions. They have to use the C calling convention because it has to correctly support inputs and outputs. You can't use structures directly, only pointers currently, because those can just be passed as integers. But it reads in the value. This function returns it to the call down here. This just automatically does the correct thing. It calls the function up there and handles the results correctly, and you can even tell it where you want the output. Give it to me in register 0, give it to me in a temporary, give it wherever, and it'll just work. So yeah, that's basically it. What I was going to say though is the interpreter took maybe an hour to write. This took basically the same amount of time, but adding in all of the support for it and the backend took much longer. Correctly supporting shifts, translating those to the AMD 64, everything. I think there were like 6 or 7 instructions that were completely done from scratch in here. Needed to support saving the results in the calls because I hadn't bothered doing that yet. Required reworking the register allocator so that it could actually handle so many input registers, because before it would just crap out after like 5 of them because it never bothered throwing them away. So there was a lot of work that had to go into the backend. But now that that's done, writing in the main goal of this was achieved. Writing an emulator using the JIT is almost exactly as straightforward as writing the interpreter, and significantly faster. And while it might not have looked as fast when running the tests, because when running the tests it was running the interpreter and the JIT at the same time, when running just the JIT like this, it takes 0.7 seconds, whereas the interpreter doing the same thing the interpreter running the same thing takes a mere, or should I say, takes not a mere, takes more, takes a more. It's about twice as fast. And this is with bad code generation. One of the advantages of this architecture is I don't have to actually touch this at all. I don't have to touch the translator. This code is more or less fine. There's a couple changes that need to be made, but for the most part, it's good. But if I just make improvements to the backend, which the front end doesn't even need to know about, it'll just start being faster out of the blue. Or one other example would be the cache. with the, I'm not even going to bother recompiling, I'm just going to scroll up. When running this maze with the JIT, it's running, zeros? 20 million instructions approximately. And there are 107 cache misses, which means since every time there's a cache miss, it adds the value to the cache. What this means is that by the end of it, there's 107 entries in the cache. So finding some arbitrary block means going over all 107 of them at worst case, an average of 50. Improving how the cache behaves would probably reduce this to 400 milliseconds. Improving the generated code would probably get it down closer to 200, if not 100. This could probably get below 100 milliseconds with a few days worth of work. And none of that requires touching the translation, which means that it's modular. All of this stuff is simple. Like calling a function like this, completely simple. You don't have to do anything except tell it what function to call, what you want to pass to it, what outputs you want. You can give it raw numbers, you can give it registers, it'll just always do the right thing. Self here is a pointer. It's a pointer in the host. It just works. It automatically does the right thing. So it meets the simple goals. It's fast to translate code. It's fast to run the code. So it meets those goals. I'm going back up to the top. It's usable for emulation, and it is usable for compilation, though I don't actually have that hooked up yet. The same assembler that generates the code for the emulator, that generates the host code, you can just take that, you can give it a different offset, take the code it produces and dump it to a file. There's no optimization passes yet. Those are going to be coming up soonish. Backends, there's still only really one. Everything is very, very simple. It's performant. You can control it completely. If you want to change how it generates code, if you want to control, for instance, if you want to control what API is used, that's going to be possible too, though I didn't implement those yet. Anything you want to change, you can do that. And it hits the modularity goal. The JIT, the translator, is completely independent of the actual backend code. It's independent of Thor. All of these pieces work together, but you can use them on their own too. You don't need to keep them together. And that's about it. So, yeah, that's it.
Okay, thank you, Noam. Do you want to share maybe some links to your project?
Yeah, sure. Let me pull that up. Currently, I'm using SourceSet as the host because it works and is actually nice, and I'm not just saying that because I'm technically interning for it right now. So yeah, if you look on SourceSet, it's very easy to find. It's probably the only thing spelling simple with a C. So yeah. All the sources are in one place. There's an LLVM-IR parser. I didn't actually mention this one yet, but I don't have the generalizer yet, but it's able to parse in the IR completely and has a very basic backend for another ISA called LIM. It has the recompilation engine Thor, Tricitrix, which is the other emulator I mentioned. That's the architecture that this one currently targets. Yeah, and everything is there. And if this bug tracker gets any actual usage, that would be nice. But yeah, I can post a link in the chat if you want, but that would mean opening it, so...
I think somebody else posted already links. I posted those. Yeah, I asked you for the links so that they can also stay in the video, in the recording. So let's switch to the Q&A view then. Just as a reminder, if you want to ask a question and you want to make sure I see it, please... tag me in it. So let's start with the default question. So how did you find out about Zig, and how long ago was that?
I don't actually know. I know how I found out about it the most recent time when I actually got into it. But I actually think I saw it 3 or 4 times before that through various links. I think people posted in some chat rooms I'm in. I'm not 100% sure. So, yeah, I don't really know how I found it. I think there was, I found the, either the Raspberry Pi bare metal thing Andrew wrote, or one of the operating systems kernel. Someone had a partial kernel written in Zig, I think. I found that by accident, and that's how I found the language, I think. something along those lines.
Okay, so we have already a couple of questions. First of all, what is meant by proof and trust? You mentioned these two terms during the presentation, and why would you want it?
Yeah. The trust thing I mentioned actually is I brought up the trusting trusts thought experiment basically, which is if you have the original idea is if you have a malicious compiler, which does when you're compiling, for instance, the login manager, it generates malicious code letting someone enter with a static password no matter your account, and when compiling a compiler, it inserts its own malicious code into it. The idea is if you can't trust the original one, you can't trust a compiled compiler with it, no matter how clean the source code is. The idea behind it is even if you can look at the source code, you can't verify that the behavior is correct because it's possible that the compiler that you're using is doing something malicious. The same idea applies here. When I'm talking about proving correct, what I'm basically saying is if I'm making an optimization to the RISC-V code, I need to be sure that the behavior before and after is exactly the same. I don't necessarily care about the actual internal details. I don't care about registers or emulated memory or anything along those lines. What I care about there is if I'm writing some Zig file.
By the way, sorry, Noam, if you're showing, let me know if you're showing something on the screen, so I can put up the right view.
Yeah, I will right now. Yep.
Okay, let me switch then. Sure, go ahead.
I'm writing some Zig code, whatever it happens to be. I want to be sure that if I have a variable here, if there's a loop optimization, it's not going to result in the variable having the wrong value. I need to be sure that the optimization is improving the efficiency of the code without changing the results. So the idea of proof there is if I can interpret the RISC-V before and after, I can map these variables to the RISC-V registers. I can say, are the values changing? Are they correct for the values that are resulting? So if I'm changing, for instance, let's say you have, this is not C. Let's say you have some value, and you're doing something like this. You're adding something like this. That's outside of a function, so CLS is complaining, but that's not really important right now. If you do something like this, if I'm optimizing this into, if I'm turning this from, or rather, let's say I'm doing this, because this is easier to exemplify, that's the wrong word, to make an example out of. If I'm adding 3 and then multiplying by 4, well, let's say I just change that into 12. I know both values. I want to be able to make sure that the compiler isn't generating the wrong number here. I want to be sure that the compiler isn't messing that up somehow. For something trivial like this, that's not really a concern. But for a lot of optimizations, they do often have negative effects. It's the same way that, or another better example would be GCC's -03. If you're giving it the highest optimization level, it can sometimes produce the incorrect code. Or not necessarily incorrect, as much as not what you intended. If your code isn't 100% perfect, the optimizations will make the wrong decision. They will assume values are present that are not, and they will do the wrong thing. They will also sometimes result in slower code. So one example of what you could do here is you could verify, is this actually making it faster? You could say, if I'm interpreting this RISC-V, how many cycles did it take interpreting it before the optimization? How many did it take afterwards? Did it actually make it faster? And if not, you can just ignore and discard the optimization entirely. So that's the basic idea behind provability. If you can prove that the result matches the input, then it means that you can actually more or less trust your code. It's similar to Rust's idea of safety. If you can prove that this code, the idea behind Rust safety, as I understand it, is you need to be able to prove that the code is doing exactly what you tell it to. Rust does that with the borrow checker. It's a tool that you use to make sure your code does what you think it does. There's similar concepts elsewhere. You can say, for instance, Zig has its runtime safety checks and so on. The idea here is to basically move some safety checks to compile time. Because, as we all know from the Zig of Zen, compile errors are better than runtime crashes. If you can prove that the code is correct, you can avoid both of those. And if the code isn't correct, if there's something wrong with the compiler itself, better for the compiler to tell you, hey, there's something is wrong, than to silently give you the wrong output. That's the general idea there.
Okay, thank you. Another question. This is from K Proti. Let me know if it makes sense or if we need to ask him to reformulate. But the question is, will the RISC-V IR support native instructions that aren't representable in the IR directly as an ISA specific instructions? As in ISA specific instructions? You're muted, by the way. Okay, now I can hear you. Yeah, please continue.
That's an interesting concept. The problem there is one of the key goals here is to be completely platform independent. If there are ISA-specific instructions that aren't supported by the actual backend, the correct option there is generally add it to the backend, teach the backend about it. But I can see how in some cases it could be useful to have sort of like an inline assembly type thing there. About that, there are some trade-offs to be considered there.
There's a question from Felix. Are you prepared for implementing the MMU for SPO Mark II emulation?
It'll be fun. I mean, all of the bus code's in one place still, so it would basically just be a modification here. It won't. The actual recompiler shouldn't be affected by it at all.
Okay. I think we have got all the questions. Well, thank you very much. That was also an awesome presentation. I think we can move now towards the end of the show then. Thank you again, Noah. I hope to hear from you again in another session in the future.
Hopefully next time it'll be on stage 2, because I plan on getting back to that very soon.
Awesome. Okay, so now, yeah, let's talk about the conclusion. Yeah, so we are at the end of episode number 3. Let's talk about episode 4. So episode 4 is already scheduled for next Sunday. That's 2 hours later compared to today. So it's gonna be easier, I guess, for people in the United States to watch, especially the West Coast. It's also going to be fairly different than today. One talk is going to be about calling Zig from the Elixir programming language, and the other will be about WASI, so WebAssembly, but the stuff that makes WebAssembly do actual useful stuff, like access the file system. Don't tell FangBS said that. Also, for the next week, I personally have 2 big items on my checklist. We got the okay from Andrew to submit a PR that changes the API of STD event loop. If you want to follow the discussion, there's an issue about it on GitHub, and I will live stream that work. Also, the intent is to, so the intent of that work is to produce a new interface for the event loop, so that implementations that make use of IO ORing and similar APIs can become a drop-in replacement for what ends up staying in the standard library. The second point that I have on my checklist is to write a better explanation for potential speakers, at least something like a guide, something that's better than what's currently in the Google form. And I will work on that also on stream. Finally, if you want to support the show, please, please consider applying to speak and spread the word. That really means a lot. Thank you to the speakers for the work, and also thank to you, the viewers. So see you all next time.
So